In today's lesson, we will analyze the insertion sort. In the previous lesson, we have already seen the bubble sort. So let us analyze the insertion sort today. Let's see what we are going to see in this lesson. We will talk about the concept, how insertion sort is done. Then we'll see the time complexity of the insertion sort. Then we'll talk about the space complexity of insertion sort. And we'll also discuss the best case analysis, the best case, the worst case analysis, and the average case complexity analysis of this insertion sort. So let's first understand how this insertion sort operates. So with the help of this simple example, let's say this is the array, this is unsorted order, and we want to sort it. So in the insertion sort, the first iteration, what we need to do is we'll start with the key element, and that key element is taken as the second element of the array. So as we can see that this is the index 0, this is 1, this is 2, and this is 3, and this is 4. So first of all, we consider this as our key element, leaving just one element before this. To the left hand side is, we'll take this as the key element. Now all the elements now all the elements before these key elements will be compared with this key element, and this key element will be inserted at its proper place. So let us see, we have only one element just before this key element, so we'll compare this key element with this one element only. So this is the left part. And now we can see that this key element is smaller than 3. We can say that this 1 is smaller than 3. Then we'll perform a swap. So in that swap, this 1 will come this way and 3 will come this way. The rest will remain same. So this will be the first pass. Right. As we can see, there is only one element just before this key element. Into the next pass, now we can see that this is updated. Let me update this after the first pass. So after the first pass, this will be updated, and now this will be 1, this will be 3, this will be 7, and this will be 6, and this will be 5. In the first pass, this was the key element. Now in the second pass, we'll increment the key element by 1. So now this time in the second pass, the key element will be this one. And now this element will be compared with all the elements which are onto the left hand side. So now as we can see, first these two will be compared. So now as we can see, first this, I'll compare this. So we'll have to compare with all these elements onto the left hand side, and we'll have to place this element onto the proper place. Now as we can see, 7 is greater than 3, no swapping is done, and 7 is greater than 1 as well, so no swapping is done. This will remain on its own place. So into the next pass, into the second pass, the sorted array, it's not completely sorted till now, will remain like this. So now we'll come to the third pass, and into the third pass, this key element will be incremented by 1. So now this key element comes to this place. And again, this key element will be compared with all the elements on its left hand side, and we need to insert this on a proper place. As you can see, what is the proper place of 6 in between 3 and 7? So we'll compare this, and we'll compare till we find that this element is greater, we'll insert it. So in this way we can see the 6 will be compared with 7. Obviously 6 is smaller, so we need to swap. We will swap, and this 6 will be shifted to this place. Then this we can see all the elements will be smaller than this particular element, so the swap will work. And after this particular swap, this will be 1, 3, 6, 7, and 5. So this will be after your third pass. Now we need to perform our last pass, that is the fourth pass. According to the number of elements, the number of elements are 5, so we have to perform 4 passes. In the last pass, the key will be again incremented, and now the key is this. So the last element is the key, and we need to insert this on its proper place. And as we can see, the proper place is in between 3 and 6. So we will keep comparing. The 5 will be compared with 7. So as we can see, 5 is smaller. This will be swapped to this place. Then again it will be compared with the 6. So it will be smaller. Then it will be swapped to this. So two swaps will be performed, one to this place and one to this place. So now you can see that the two swaps are performed, 5 just to insert 5 onto its proper location. So after the fourth pass we can see that this comes to this place 5, then this will be 6, and lastly this will be 7. So this is how the insertion sort is performed. So now consider this pseudocode and analyze the time space complexity. So this is a simple pseudocode that represents the concept of the insertion sort. This outer loop is for the passes for each pass. Here we'll store the element as a key element, and then this inner loop will perform the placing of the key element onto the proper sorted into the proper place, so that this list will become a sorted list. So let's analyze the complexities, as this is a loop from j is equal to 2 to n minus 1. So the complexity for this will be order of n. Now this is a simple statement, so this will be order of 1. Then this is another assignment statement, order of 1. This is the inner loop. So this is the inner loop, although this loop will have the complexity of order of n, but as a whole this will be n square. So let me write here order of n, and this inner loop will result, so the time complexity will result into the order of n square. Now this is order of 1 inside the loop. So this is a loop to place the key element onto the proper place, and this is another assignment, order of 1. This is to increment the key after each pass. So now as we can see that this is the inner loop, so the order of this insertion sort time complexity will be order of n square, right? So the time complexity for insertion sort comes to be order of n square. What will be the space complexity? Let me talk about the space complexity also. For the space complexities, we'll take the variables. As we can see, this is j. The j variable will require one space. Let me write all the variables. Let's say j will require one space. Then this array will require n size. The key variable will require again 1. The I variable will require one space. So I will require one space too. As in all, we can say that the maximum size for the space is occupied by this array. So the space complexity for this insertion sort comes to be of order of n. Now let's talk about the best case, worst case and average case analysis. What will be the best case? The best case when the elements are already in the sorted order. So let's say if the elements are in the order 1, 2, 3, 4 and 7, this is already sorted. So once we have the already sorted order, then only the passes will be required, but in each pass there will be no such this loop, no requirement of this loop, because there will be no swap performed as all the elements are already into the sorted order. So this inner loop will have no concept of this. There will be no comparisons, there will be no swapping. So for the sorted order, once the array elements are already in sorted order, the time complexity will depend only in this outer loop, that is for the passes. So the best case will be of order of n. So this is the best case time complexity, that is order of n. Now what is the worst case? When we have the elements completely in reverse order. Let's say 7, 5, then 7, 6, 5, 3, 1. So if the elements are completely in reverse order, this is called as the worst case. And in that sense, we need to have passes, we need to have placements also. So both these loops will work, and we'll have the complexity of order of n square. So this comes to be the worst case complexity, and this is your best case time complexity for the insertion sort. And the average case is also order of n square. So this is also the average case. Average case is any case which is somewhere in between the best and the worst case, or we can also calculate the average case complexity by finding out the complexities of all the cases and then dividing it by the number of cases n. So the average case complexity for the insertion sort is order of n square. best case complexity of the insertion sort is order of n, and the worst case is order of n square. So we have covered today the concept of insertion sort, how insertion sort happens. We had already seen the pseudocode. Then we had talked about the time complexity, space complexity, and we had discussed the best case complexity, worst case complexity, and average case complexity. I hope you have understood the analysis of this insertion sort. In the next lesson, we will talk about the selection sort and we'll analyze selection sort algorithm. Thank you so much.